Sorry. We started the recording, sorry about that.
Oh, sorry, you started late. Okay, sorry. So, and then we're gonna finish with a summary and conclusions. So, soil structure interaction. What is soil structure interaction? It is a process in which the deformations of the structure will affect the response of the soil. And in turn, the response of the soil will affect the deformation of the structure. So it is important. Let's see what we have. First, some structural engineers, okay, may consider, let's say, analyzing their structure, assuming that we have supports here. So basically, they're going to close everything, assume, let's say, that this building is built on rock. No deformation, no soil structural interaction. So definitely, this will going to entail no interaction. If we have seismicity here, earthquake or whatever, we're going to have a big problem. The performance will be so different, okay? Then, one step ahead, one step further will be to represent the soil using springs. So to represent the stiffness of the soil and its effect using springs. So again here, we didn't simulate the real soil structure interaction, we just took part of it. So this we can say that it's halfway, not halfway, let's say 10% or 50, 20% along the thing. Then if we consider the entire thing, the full soil structure interaction, this is the right thing to do. And actually this we're going to give you the real performance or the real prediction of the performance of your structure. Okay, so here you're going to consider the full interaction. So this is our journey through the soil structure interaction. Okay, so we can totally ignore it, wrong results, bad prediction, not good, or we can consider it partially, but again, partially means some part of it. So it's not good, but let's say 10, 15, 20% along the way. And of course, if we want to consider everything, we need to consider the full soil structure interaction. Okay, however, every one of this, we're going to come with its cost. So the numerical cost and the numerical effort and the expertise of the numerical modeler is very important here when we consider the full soil structure interaction. So let's continue. So in this lecture today, we will gonna explore the effect of the soil structure interaction and the predicted performance of two special geotechnical problems. So I just chose for this lecture two different problems to show you the power of the soil structure interaction. So the first problem here, we're gonna involve investigating the effect of the soil structure interaction and the employed conservative material model on prediction of the behavior of earth pressure balance shield driven tunnels, utilizing a case study, real study of Metro Line 2 in Shanghai, China. In the second problem, we're going to do basically the same thing. We're going to investigate the performance of integral abutment bridges. However, we're going to use a case study from New Brunswick, Canada here. So let's start with the tunneling problem first. So this is here the map of Shanghai here. So this is line 1, and the green one here is line 2, which we considered in our analysis. So after they excavated or driven their line 1, they went into line 2. So if we explode this area in here, just magnify it, we're going to see that this is your line 2 here. Okay, so and these are the boreholes available along the. Okay, so as we see, we have so many soil layers in here. Okay, mostly soft clays, soft soils, silty clays. So in general, soft soils. And the tunnel itself, it was composed of 2 tunnels. Okay, so we have tunnel 1 and tunnel 2. Okay, and what we have in hand is the settlement readings or monitoring program, results for settlement, pore water pressures, lateral movement, and earth pressures. That's what we have, as we're going to see later on. So let's refresh our minds. What tunneling involved, or this earth pressure tunneling involved. So if we look into here, this is a tunneling machine. It is kind of conical shape a little bit. And we have here the face pressure. And as it excavates here, the residual or the products of the excavation will be just conveyed in the conveyor here outside in here. And as it excavates, create area and moves in, we're going to create a void space to install the new segmental lining. And then after we put the segment, each segment, okay, along the ring, we're going to start injecting grout. Okay, so if we look into this from this side in here, we have face pressure. Okay, and then we have our lining and we have grout in the tail here. Okay, this grout is not hardened immediately, so we have fresh grout, and this fresh grout will harden by time. Okay, as we proceed. Okay, so this is general the thing. So in order to start the model, we use the concrete model available in Plaxis. This concrete model was just new. This work here that I'm presenting, we did it, I think, 3 years ago. So the concrete model was just new. So we have first to validate the model, make sure that the model works fine. So we validated the results through tests done by V et al. For plain concrete in 1996, and another test by Mansour et al. In 1999. Okay, so here we have the strain versus strain, and we have those kind of gold dots represent the test results, whereas the continuous green line represent the predictions of the Plaxis 3D. So it is beautiful. You can say that it's match beautiful. We were able to capture the performance of the concrete, even post cracking, which is very important in here in this region here. So it is amazing. Actually, I had to double check it a couple of times to make sure that everything is fine with my students right now. She's Dr. Anna Maria Zaki. And this paper is published in the Transportation Geotechnique. I can give you the link at the end for the paper to enjoy reading it. So also, this is what we are showing here is the 3D mesh of the problem. We have several different layers, as we said before, and we modeled 42 meters of this tunnel in the third direction. Okay, so we use the hardening soil model. So we were going to see which soil model will going to give us the best prediction. So we considered the hardening soil model. The hardening soil model with small strain stiffness, okay, the modified camp clay model, and the soft soil model, all of in Plaxis. The soil parameters utilized for the 4 consecutive models in short and long-term conditions were obtained from the conducted laboratory experimental results. So we have this results, and accordingly we obtained all of the required parameters for each of the models. So here I'm just summarizing what this entails in 3D. So as we said, we have face pressure here that will be applied, okay? And we have the weight of the conical shape earth pressure machine, okay? This is a shield of the machine. And as it progresses, as the machine progresses stepwise, okay, as it installs the new liner ring, the new ring, the grouting will gonna continue, we're gonna start, sorry, with fresh grout, and then as it proceeds, this grout will be hardened, so it will be assigned the hardened ground properties. Okay, and then the process will gonna just repeat till we finish it. Just for your information, each run took from us on a very powerful server that we have in our group. It took us 7 days continuous. Why? Because we are modeling everything. We are modeling the true construction procedure. We modeled as well the connection with the, so we modeled the segments, the tunnel segments, and the connections with the ports. So everything is being modeled in here in details. Okay, so let's see what are the monitoring results and their comparison to the predictions of our model. So we have the results of the surface trough after 1 month and after 3 months from the general height time. Okay, so the experimental results are shown here in this orange squares. Okay, in here. This is after 1 month and this is after 3 months. Okay, the black continuous line represent the hardening soil model with small strain. The brown one represent the predictions of the hardening soil model, whereas the blue one represent the modified can clay, and the green represent the soft soil model. As we can see here, the best one of them that mimicked the performance of the settlement trough is the hardening strain model. Okay, so after 1 month, the predictions were within less than 0.5%. Okay, 3 months, same. Okay, however, here for the 1 month, the hardening soil model was 4%, the maximum. Okay, for the soft soil, it was 27%, and for the modified can clay, it was way, it was 32%. Actually, in the 3 months, things get much worse for the other ones. So from here, we can say that the hardening soil model with small strain outperformed the rest, was the best. Let's move to the pore water pressure. So this tunnel here was fitted with different piezometers at different depths to monitor the progress of the pore water pressure with time. And here we have the results of 200 days or 180 days of monitoring. So basically 6 months of monitoring from construction to the end. So here we have the predictions of piezometer 1, 2, 3, 4, and 5. So in a different location over the tunnel here. So again, we can see that the performance of the, especially here the tunnel here, the performance of the hardening strain model with small strain is the best, as we see. Okay, same thing here for the lateral movement of the tunnel and the transfer direction. Okay, so as we see again here, this orange squares represent the field case study, whereas our black here represent the hardening soil model with small strain, and we see that it was the only one that was able to mimic the lateral movement. By the way, here we are talking about 2 or 3 millimeters, so it's very, 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 very precise. So when we have this difference here is less than let's say less than 1 millimeter or so. Okay, so the prediction is great. Also, this liner was instrumented with different pressure gauges, pressure cells, okay, over the tunnel, and here are the predictions again during construction of the different cells. And we can see a perfect match, excellent match of the pressure that was obtained by the hardening soil model with small strain. Okay, so here this showed us the importance of the soil structure interaction. We were able to mimic the behavior exactly for this very complicated tunneling problem. This is tunneling in very soft soil, so everybody who works in tunnels knows that this is very challenging problem. Okay, however, the powerful of soil structure interaction, the power of soil structure interaction, and the use of appropriate soil model was able to help us to predict the results very, very nicely. Okay, so let's move to the second part of this lecture, which is considering the Industrial Park Route 7 underpass integral abutment bridge case study here in New Brunswick. So let's introduce what is integral abutment bridge, because maybe some engineers listening to us right now don't know exactly what is the behavior of it. So they are Bernoulli structure in which both of the superstructure and the substructure moves together into and away from the backfill to accommodate translation and rotations with no expansion joint and bearings. Everybody works in the bridge industry knows that bridge bearings are and the connections here are the worst. So they need lots of maintenance. It's very costly, okay? Especially in countries in the north here, like United States, like Canada, like Northern Europe, whatever, we have huge fluctuation in the temperature, and accordingly, those the we are gonna have use de-icing salts and stuff like this. So accordingly, we need frequent maintenance, and this is huge cost. Accordingly, they moved to more or less to the integral abutment bridges, where the structure and the abutment of the bridge are being poured together, are working as one structure. So eliminating the need for any joints or bearings or for whatever. Okay, so also, the simple geometry of the abutment with single row of pile, which will be very typical, and it results in a very fast construction as well. Because basically, as we're going to see in the next slide, we're going to just use one row of H piles, and that's it, and we support our abutment on this. So again, it's very, very, very useful to eliminate the expansion joints and the bearing, which we're going to significantly reduce the construction and maintenance costs. So, in general here, integral abutment bridges are characterized by their complex soil structure interaction of the abutment wall and the foundation as they are subjected to cyclic loading. So, let's say in the winter, the concrete will shrink, right? So, the structure will gonna move away from the soil, and this will gonna constitute more or less an active earth pressure. However, during the summertime, the concrete will gonna expand, and accordingly, you're gonna push on the backfill soil and will be in its passive mode. Okay? So, the objective of this part of the lecture here will be to understand the effect of the thermal movement of the bridge on the soil structure interaction. We're gonna utilize a two-dimensional finite element analysis. Okay? We will also explore the effect of the employed soil model again to see its effect on the prediction of the earth pressure within the soil mass, as well as the earth pressure acting against the abutment, which undergoes cyclic loading. Okay, and also in this section here, we're gonna show and we're gonna demonstrate that the simple Moore column or the elastically perfectly plastic soil model that's being used frequently by several engineers to model such problem is not good, and it will not gonna accurately describe the behavior. It will not be able to do this. And we need more advanced soil models like the hardening soil model and whatever to be used. So let's talk about the case study that we have in hand here. So this is our apartment here, okay? So on this apartment here, rests a girder, which is 1800 millimeter deep girder, so it's a large girder here, that supports the bridge deck here, which consists of 225 millimeter of deck slab overtopped by asphalt. And then at the back here, we have the approach slab, and we have draining material in here, and then we have a backfill, just the polo backfill to backfill behind the drain material. And below is supported on H piles, okay, suited in their weak axis. So we give a flexibility of movement, seasonal movement of the abutment. So this abutment here was heavily instrumented with strain gauges, with thermocouples, with contact pressure cells, tilt meters, deformation meters, and you name it, was heavily instrumented. So we have, so this will gonna help us to develop a comprehensive model that we can validate it using several things, not only one. So basically here, this is the wall, the retaining wall. So we have the earth pressure at 3 levels, and we have the tilt meters here at 2 points here, okay? This is the monitoring results that we have. So here, this is the change in the translation and the movement of the apartment versus the time. Okay, so this direction here below means that the apartment moved toward the backfill. So toward the backfill, this means that we are in the summertime. Okay, up here, this means that the movement was away from the backfill, or it's in active mood, means that we are in the winter time. And here, this is the variation of the temperature. As we see, the temperature varies in the summertime of near 30 degrees or maybe 31 degrees or so to a typical Canadian weather of huge -0. Okay? So the changes and the pressures as well, we have it here for the different sensors. Okay? So we have two models here, soil models that we used. The first one, which is the elastic perfectly plastic soil model. We all know this model. You just need your elastic model E, and accordingly, you need your phi and C, and that's it. So it is perfectly plastic after. Okay. The second model, which is the hardening soil model, which is suitable for this kind of loading, especially because it has three different stiffnesses. One stiffness, E50, that represented a triaxial loading stiffness, okay, which we're going to determine the magnitude of both the elastic and the plastic strains. We have E odometer, which is the odometer loading stiffness as well, which we're going to account for the plastic strains due to the primary compression. And finally, we have the E unloading, reloading, which in conjunction with the Poisson's ratio will be able to determine the ground behavior under unloading, reloading conditions. So basically, this soil model is comprehensive in terms of the nature of the loading itself, the soil that will be loaded. So we know that the stiffness of the soil during loading is different than its stiffness during unloading. Constrained stiffness is different than the stiffness in triaxial. So this soil model here is capable of addressing all of this. So we developed two Plaxis models, okay? We apply to those Plaxis models here the cyclic thermal displacements, okay? And we monitored the earth pressures, okay? We have one model, okay, that was utilized using the hardening soil model, the one that we believe it will be predict their behavior better. The second model, which used the Moore column, that soil model, or the elastic perfectly plastic soil model, that we want to demonstrate that is not shear. So these models follow the same geometry layout construction procedure of the full-scale abutment, and the results were compared with the field measured earth pressures. Okay, so stage construction very quick. First, we install the. Oh, sorry. Just give me that. Still only 2 minutes or 3 minutes. I don't want to overrun, but let's circle that. So then we simulated the excavation. Then we placed the pile platform. Then we put our pile in sand. Then we're going to continue with the whole construction sequence. Okay, till we have at the end here our full about with the loads coming from the main structure. Again, you can read the paper here. I'm going to send the link for the paper. You can enjoy reading it with my student, Mr. Francois Duguay. Okay. So in this problem here, this is the applied displacement. So it was superimposed displacement that represents the monitoring cyclic displacements. And then we were going to read the pressures, earth pressure in the back of the wall, and compare it to what we have. So in here, we have the results of we are showing the results of the second model, which is the Moore column. Okay, so here we have the predictions of the field. Okay, so in the first year, we have the predictions from 3 years. Okay, in green here, we present the first year. In purple, we present the field results of the second year, and in red represent the field results in the third year. Okay, the Plaxis result of the respective things are in dotted lines. Okay, and this are presented along the height of the abutment, and here we are presenting the seasonal changes of the earth pressure, so the difference or the movement of the earth pressure. So, and these are the three locations that we measure the pressure at. So as we see, those three are the earth pressures in reality, and this was the earth pressure that we obtained using the Moore problem. If we consider the error or the difference in predictions here in the first year, second year, and third year for the 3 points or the 3 locations, we're going to see that we had almost an error, estimated error of about 33 or 34%. Huge, definitely not acceptable. Let's see when we considered a better prediction model. So as we see in here, the predictions of the Plaxis and the field results are almost identical. Only difference here is 3-4 kilopascal, which is basically nothing in the difference. The error is less than 10%. Okay, and basically, actually, this is at the very lower point. The other points, the error are almost matching. There is almost no error. We're talking about 1%, 2%. So this is perfect prediction. So just to summarize and conclude, okay, so we presented here a detailed finite element analysis using Plaxis 3D and 2D to examine the soil structure interaction performance of 2 special geotechnical problems, the tunneling problem and the integral abutment bridges. What we can take from here is that for the tunneling problem, we consider 4 different advanced soil conservative models. However, the hardening soil model small strain was superior to the other models under consideration in modeling the soil behavior. This superiority is attributed mainly to the ability of the model to mimic the variation, the stiffness that accompany the changes in the strain level, especially at small strain levels, which is very important in tunneling problems. However, for the integral abutment bridge problem, we showed that the simple elastic, perfectly plastic Moore column model that's being used frequently by engineers to design such problems here is not capable of simulating the soil behavior during the cyclic loading and unloading cases, and that the hardening soil model was a better soil model to use. The maximum value of error of the hardening was much lower than the 12%, okay? And whereas the error for the Moore column soil model was 34%, 1/3. So definitely it's not. So thank you so much. It was my pleasure today to be among you and to present. Thank you so much.
Thank you very much for this amazing lecture.
3-4 minutes extra. I'm so sorry for that.
No. Any questions? If you have.
Hi, Mahmoud. Yes, I have a question.
Yes,
Hi, Mohammed. Go ahead.
Hi, Doctor. In the tunneling part, I was wondering, like, in your model, do you consider the lining as a waterproof because you add like the grout between the soil and like the concrete lining, or you allow it as like a kind of a drain because of might be like some permeability or so?
Yes. No. We assume it's embedded, so there is no water.
Okay. Okay. And also, like, Doctor, is there any effect, because like I found that there are 2 tunneling, is there any effect like for one tunnel on the other, or like the distance was like wide enough?
Exactly. Maybe I missed presented this or presented very quickly. So first we mined the first tunnel, was mined in, and then we put the second tunnel. The effect is not that huge because the tunnels were located 18 meters away from each other. So almost that was 2.5 meters away from each other. So the effect was not great. But if you don't tunnel, your prediction will be of less match. Okay.
Thank you, Doctor.
Yeah, you have to consider that thing. You are very welcome. You know the Muhandisin building that has some problems, maybe last year, whatever, would have been told pretty much with such modeling technique. So if they modeled everything before they tunnel it, in details, like what we did with the Chennai case here, this could have saved the building, which is multi-million building.
Yeah, this is the one at Zamalek.
Yes, in the Mag. Sorry, I said once. I'm from Alexandria. So one place, Cairo.
Thank you very much for this interesting presentation.
You're welcome.
Ahmed, I think you need to ask a question.
Good morning, Dr. Hany. I hope you are doing well during fasting. I have two quick questions.
Please.
The first question is related to the forces applied to the tunneling in the first part of the presentation. I observed that you applied a drilling pressure during tunneling, but I'm wondering if there are different forces were applied to the tunnel.
So the tunnel in the face pressure, you have a face pressure which is linearly increasing with the depth, of course, okay, to resist the pressure from the soil. Also, we consider the own weight of the tunneling machine itself, okay? And then you have the jacking forces that being applied. So you have the jacking forces, you have the face pressure, okay? And then also you consider the grouting pressure as well. You consider that grouting pressure. Have I missed any? I think that's it. I think that's it. You can refer to the clear reference of this case study. Actually, it's very nice, not because it's my work, but really I enjoyed it. It's very nice case study, and it's published in Transportation Geotechnique, I think, in 2019 or 20, I'm not sure. 2019, and Transportation Geotechnique 2019. Anna Maria Zafin and Hany Naggar.
Yeah, because what I witnessed during the presentation that you only mentioned the face pressure, so I was wondering, because according to my my work with tunneling, that we always apply jack thrust, and we apply also the segment, which is the lining pressure. And in case if there is like a shield, like a steel shield, until we apply this pressure also.
Yes, we simulated this. We simulated all of this.
Yeah.
My second fact, because it was just I'm presenting two cases, two cases, and the time is only allowed is only half a minute, so that's why I was a little bit fast. Sorry for that.
Thanks, Doctor. My second question is a general question. It's related to choosing the numerical model or the constitutive model for the analysis. Usually, we have like a lake of parameters that require for the sophisticated model, for the sophisticated models. So I'm just curious, how can we like choose these parameters, and how we can control the uncertainties of the finite element, especially with this lake of soil parameters?
Very good question. Very good question. So first, what you need to do, you first need to validate your model first, mechanically. So you need to consider case study that you know the results and the monitoring results that you rely on, and the soil are more or less closer to your soil. Okay? So let's say if you have tunnel mainly and clay, whatever, you're gonna go with the London clay cases. You have several of them. Then you're gonna, after validating your model, you know that your model mechanically works fine, everything is fine. You're gonna start looking into the parameters, soil parameters for each. You will gonna try to have, of course, for such projects, you have the luxury of ordering A-class soil testing. So you're gonna have lots of tractions. You can get this. The contractors cannot say no, we don't have this. We are talking about billions here, right? So you have a full suite of soil testing that you can apply. When you are in doubt or when you are missing some data, you're gonna go with some correlations for the similar soil. So you need to dig a lot in the literature. So what I'm always saying that if the job is assigned, let's say 100 hours to do the design, okay, you need 30 hours of reading literature, what others did in the same soil, the same conditions, what problems they faced, and what's going on. So you need to educate yourself, and not only, let's put it this way, refresh your mind for every project. So you need to read and read and read and read and read. So it's very, very important to do this. And this is the only way that we have. Okay?
Okay, thank you very much. I have a related question to this part, which is, if we are performing or conducting like a centrifuge test or a shaking table test, usually when we start to calibrate or validate the numerical model, there will be also uncertainties about the setup of the test and also the measurement, especially if we are working with the soil structure interaction. We will find there is a lot of disturbance, especially after installing the structure. So when I'm like, if there are a lack of measurement, especially after installation, and I am calibrating the numerical model. So my question is, there could be uncertainties from the measuring of the parameters, but what could be other factors that can affect, or I can like accept a threshold for the errors in the numerical model?
Okay. Look, what you cannot forgive is the construction sequence. So you need to know exactly the construction sequence, even if it's wrong, let's say, but you want to validate, right? So your model has to follow the same construction sequence that was done in the centrifuge. The problem with centrifuge, it is so sensitive kind of testing and needs lots of experience. So for example, I had one of my PhD students, Dr. Naim. He did centrifuge and memorial here, and it took considerable time in order to understand how the system works and how we're going to model everything, and what kind of scaling effects would be involved. And there is always a kind of trade-off. So scaling effects, yes, always will be there. But otherwise, we don't have a full scale of the problem to consider. So having the problem in full scale is going to cost billions of dollars. Nobody's going to invest this money in this. So what I'm left with is that I have to do with centrifuge. So I need to have good experience with centrifuge model. It's very important. When you move to your numerical modeling part, you need to have as much information and data as possible. If you are lacking, let's say, key important information, so with all due respect, you lost the test. It is a test, yes, but it's useless. Let's put it this way. So at least you need some reference data. Let's say you need to have some CBT results, which is commonly can be conducted with centrifuge, let's say. And accordingly, you can use such CBTs, let's say, to correlate to the, say, soil properties that you need for your model. Okay. Also, there is 2 or 3 papers by Naim and Naggar, and the 2 Naggars, not only one Naggar, was Naim, Hany Naggar, and Hisham Naggar. So you're going to find 2 or 3 papers. We modeled the microbial raft interaction, okay, using centrifuge models. So I think this would be very useful. Just read it, and if you have any questions, just shoot me an email. It would be my pleasure to have this session.
Thank you very much, Doctor. Thank you for your splendid presentation. And as always, you impress us.
Thank you so much. Thank you.
Thank you.
Okay. Anyone have a question? I think Ali need to ask.
Okay, sure. Sorry,
Yeah, so there's no question. Thank you very much for this amazing lecture and your response. Yeah, thank you.
Pleasure. Thank you so much. جزاكم الله خير. رمضان
جزاكم الله
مبارك.
خير. علينا وعليكم إن شاء الله رب العالمين. So the next lecture would be with Dr. Ahmed Abdelrazik. Ahmed is here, right?
Hey, assalamu alaikum.
Alaikum
Hey,
salam.
Mahmoud, how's it going? Hey, guys. So should I just get going? Share my screen?
Yes, so I have to present you first.
Yeah, go ahead.
Dr. Abdulrazik is currently a geotechnical engineer at Hatch, serving global and national clients in mining, infrastructure, and energy business sectors. He received his PhD from Queen's University, where he explored the usage of GCLs in contaminate applications. Earlier, he worked for Dar al Handasa Cairo, where he tackled multiple infrastructure projects in the MENA region. So Ahmed, go ahead.
Sure, thank you. Hey guys, so I'm just gonna share my screen now. Okay. All right, so today's topic would be about the geotechnical insights on railroad design. I just want to make sure, are you guys able to see the screen properly?
Yes, we can see the screen, but I think we don't see the presentation mode. I think you have to, go ahead for the slideshow.
Perfect.
Yeah.
Okay.
Perfect.
Yeah. I think in today's topic, I just wanted to touch on few geotechnical aspects that we need to consider in railroad design. One of the booming topics, I guess, with today's infrastructure development. So whether developed or developing countries, it's always a huge investment with today's trend in public-private partnership projects. Also in a lot of mining projects, you're always requested to have some sort of a rail spur or rail connection to be able to transport a lot of the products of the mining processing in and out of the mining site. So in today's topic, we'll just start with a brief intro about a typical railroad design and the main components we have. So we usually have a rail, the rails placed over the ties or the sleepers, and then we have what we call a track bed. This track bed is mostly known as a ballast sub-ballast granular material, but as I'll show you guys throughout the presentation, there can be different formations and different types of track beds, and then those track beds will just transfer the load of the train into your subgrade. So the main components we have is the rail and sleepers, the track bed foundations, and this is where your input would be required from a geotechnical point of view. And then your subgrade is basically your founding soil. One of the issues I always came up across when I'm reviewing work by others is sometimes you focus a lot on designing the track bed, but then people tend to overlook how these loads will transfer into the subgrade. So always remember that your subgrade is your founding soil. That's the soil transmitting, or this is the soil that need to be able to carry and sustain the load for the design period of your railway embankment. So just an idealistic approach when dealing with this problem is you have traffic data. This is very, very important, very vital, because it means a lot of money. And this is one of the areas where there is always deficiency in information from usually the client side as to the expected traffic data. So it comes back to using common knowledge, engineering knowledge, as well as digging up data when it comes to the expected traffic data for railway alignments with sort of similar properties and characteristics to the one you're dealing with. Soil properties, very important. You can achieve these by having an advanced and develop a proper field and laboratory testing. So know what you're doing, know what you're looking for, and select the samples that would be representative of your site so that you can have a better judgment on what type of material you're dealing with. Simulation, semi-empirical, there is a lot of semi-empirical approaches, whether it's numerical, so numerical softwares that are developed using semi-empirical methods, or advanced numerical methods, which again requires more sophistication. You need to deal with a lot more parameters, and you need to understand what's the significance of these parameters. And then your output is basically what you're hoping to achieve by the end of your design. So I'll just try to break down these topics and talk a little bit about each one. Again, briefly, I didn't mean it to be like an intense lecture, but the idea was to give you guys an insight as well as touch upon the key issues that you have to be aware of when you take a similar job. So the static wheel load is something that usually get depending on the train type. So when we talk about trains, we're talking about locomotives, we're talking about the rail cars, typically that carries passengers or carries like freights along the rail track. Luckily, because it's a very standardized profession, I guess, the rail engineering, there is a lot of tables, there is a lot of manuals. Just to name few, the British Standard, the ARIMA, and the Canadian, like the CN rail standards, they provide tables that discusses the static wheel load depending on the load you have, depending on the type of train you're using. Then the impact factor, and that's when the empirical approach kicks in a lot of the manuals and the guidelines. And the idea is how to switch your static load into what we call a dynamic wheel load. And the purpose of the dynamic wheel load is basically to consider the fact that there is, it's a moving load. So it's something similar to the line of influence. For those of you who have interest in structures, probably came across this a lot. Or to consider the impact of the, magnification of the static load to encounter for the additional stresses due to the dynamic movement of your train on the track bed structure. Different wheel diameters. Wheel diameters are very important because they actually get into your impact factor, and the impact factor can vary significantly. So you need to be aware of like the wheel diameters that you're expecting on your rail track. I think a lot of studies have been done to kind of see what's the critical loading condition, and it was found that the condition that I'm showing here at the picture at the bottom, where you have basically 4 axle loads. So you count the wheels here, 1, 2, 3, 4. So each wheel is connected by an axle. So in that situation, this is the more critical criteria from a geotechnical and actually from a structural point of view when you're designing your rail embankment. So the maximum rail seat location, very important, and just keep this picture in mind, the 4 axles that we have here. Yeah, this one. Other 2 key factors also for the traffic data is the traffic tonnage and the number of repetitions. And I thought, this would be just an easier way to kind of go through them and see their significance. So typically in a wheel load for like some of the like common rail cars, you're dealing with 36 pound per wheel. So this is the static wheel load. And then for one car, you can see that given the critical scenario or the critical simulation of like loading on the embankment, you have 1, 2, 3, 4 times 2, we have 8 wheels. So this would be the total load that you have at the critical situation, which is equivalent to 140 ton per rep. The number of repetitions, you can assume that, just for simplicity, 200,000. And I use this just for the sake of the exercise, but usually you're able to, when you have rigorous traffic data, or when you're dealing with mining production, for instance, where you have a certain production rate per annum or per year, and you can know that how much the train can transfer per trip. So you can know how many trips that the train will take over your track, and this would be the number of repetitions. And then basically the multiplication of these two would give you the traffic tonnage, or the TI. Very important parameter, and it's very important because it helps you classify how critical the railway embankment you're dealing with. Usually up to 5 MGT, million gross ton, is considered like a light application track. Above 5 is considered like one of the more critical or heavy track application. So the second item that you need to also have before you start designing is the real pressure on your track bed. Throughout like the different tasks I have handled, there is usually different methods to estimate that track bed pressure, mostly from the wheel load. There are a few programs, just to name few, like CanTrack, one of the readily available, easy to use tool to help you estimate the real pressure. And in today's topic, I'll just touch upon 3 different methods in more details and show you guys the equations and what are the governing parameters. Keep in mind that our idea is we have train load. This train load is transferred through the rail track onto the ties, and then these ties transfer the pressure into the track bed. So just keep this in mind as we go through the presentation. The ARIMA, that's the American Railway Engineering Manual. They provide plenty of equations to calculate what they call the ABP, which is the average ballast pressure. I picked one of the equations here because it directly correlates the ballast pressure to your wheel loading, your impact factor, and the distribution factor. And that distribution factor is basically to consider the fact that your wheel load will be distributed as a uniform pressure on your track bed. And then there is also another enhanced method in the ARIMA. And in this method, you basically consider the rail ballast interaction. And so this is sort of an advancement to the previous method. And if you guys use this method, the ARIMA, or you try and follow this method, you will always realize that this method gives you probably 25 to 30% lower pressure on the track bed, because it considers how the parts act together. Remember, you're designing a structure, although the rails are usually either typical from like the specifications, like the track specifications, or they come from like the structural / rail team. Keep in mind that the rail with the sleepers, they act as one body, and that body transfers the load into the track bed. So in this enhanced ARIMA method, it considers the rail stiffness and deflection under applied loads. And the way the load transfers is you have the P, which is our dynamic wheel load, the static times the impact factor, and then it travels to the ties, the horizontal sleepers we have here, and then from the tie, it goes to the top of your ballast layer. Just few simple equations here. Again, generic equations, but they just convey the message. You have a distributed pressure on the tie, and that would be the rail stiffness times the rail deflection. And these are rail stiffness. Again, there is a lot of interpretations as to how much would the rail stiffness be. There are a lot of field tests that are usually done, or typical rail stiffness that's recommended depending on the million gross ton per year that you're dealing with, which is the traffic tonnage. Your rail deflection, the output of this gives you a distributed pressure. Now remember that this pressure is uniform pressure. To consider a critical case, you need an influence factor, and that brings us back to the line of influence models, the fact that you have a single wheel moving along the rail track. So again, you rely on the manuals like ARIMA and see, how to get an appropriate beta factor to get your P max. And then this P max, when you multiply it by the tie spacing here, you're basically converting this into a load over your tie. So this is the pressure because you had that pressure linear, and then you multiply it by the spacing A, which is the spacing between the tie and the other tie, center to center. This converts it into a horizontal or into a uniform pressure acting on the sleeper. And then from that F max, you basically divide it by the area of the sleepers. And that schematic here hopefully explains things much better. But as you see here, you have a maximum pressure and you don't have a uniform pressure all over. You have an effective length of the tie that actually sustains the majority of the load. And then you have an area here where the surcharge significantly drops. So you divide your maximum force by the effective area and you get your average ballast pressure. So when you do this approach, the enhanced one, and you compare it with the old ARIMA method, you will realize that usually this method tend to give you 25 to 30%, at least what I have seen, for the average ballast pressure compared to the typical ARIMA method, although it needs more input. So, and that input is probably what makes it a little bit enhanced, because it considers how the parts work together and how they impact the pressure on the track bed. Now, when you have this load, which is the surcharge acting on your ballast, now you can start thinking about how the track bed will look like. So there is track bed type. This is something that you need to think of, you need to specify, and there is the thickness of each of these components. So the granular track bed is the traditional one. That's very common. Sometimes it's not very economically efficient. Just keep this in mind. So you have the ballast overlying the sub ballast, and then your subgrade. Now, bedrock is not a necessity here. Sometimes a stiff soil compared to the overlying soil, or sometimes just the natural damping that would happen when the surcharge transfers the load with depth. So just this bedrock, don't think of it as a bedrock geologically, but it's more like a refusal surface, or a surface where the effective stress is not did not like increase significantly due to the overlying load from the ballast, sub-ballast. There is the asphaltic track bed, which is basically a ballast and asphalt binder that provides some tensile strength and distributes the load better onto the subgrade. So you basically substitute the sub-ballast with a layer of asphalt within your ballast layer. And then a combination, if needs be, you might have a situation where you have ballast intermixed with asphalt and then overlying a sub-ballast and a subgrade. So the type is, again, it's the cost, the lifetime of the project, and the specs or the specifications that you have for the project, and if it provides any guidance as to what type, and also the familiarity of the available contractors, like local contractors within the area you're working. The granular material thickness. Again, plenty of equations. Uh, Interestingly enough, like the famous like Buzanisk equation actually provides a not so bad formula to get the granular thickness, and in most times the numbers you're getting from Buzanisk are quite close to other approaches. The one common method that's used at least within like North America would be the Talbot equation, and in this equation you have stress at the bottom of the tie, and you have the allowable subgrade stress. So this is your bearing capacity right there. So you're going to be aware of the soil conditions, and like what sort of strength that you're expecting from your subgrade to be able to get the support ballast. The idea is the thickness that you're using here will govern how the pressure will be distributed within your track bed. Um, and then one of the methods that I think is one of the most like robust design approaches out there, and it touches upon few key concepts that we geotechnical engineers are always interested in when dealing with embankment design. Um, it considers the impact of repetitive loading, and it's valid for soft grain subgrade. At least this is how they develop their approach. But with the right amount of data and the right information, you may be able to extend it, but be a little bit cautious if you extend it to other like not soft grained like silt clay and intermix, for instance, like glacial till and stuff like that. The good thing about this method, Lee et al., is it introduced also the serviceability and the plastic strain limits. And that's, again, concept that is not quite appreciated by other methods. So in Lee et al., you're dealing with two modes of failure. We have the progressive shear failure, and that's basically when the load is excessive compared to the capacity of your subgrade, and then you start forming this like rutting, basically, of your subgrade due to the excessive settlement and shearing along your subgrade. So it's very similar to like a bearing capacity failure. And the plastic deformation is the second mode, and that deals quite a lot with your serviceability. A matter of fact, sometimes when people overlook the plastic deformations along the rail track, and when they do maintenance, they keep increasing or adding more ballast into like the fouled areas or the areas of deficiency or excessive settlement. And what this does is, because you've exceeded the plastic limit of your soil, you end up getting these like concave shapes vertically or like transversely, and also longitudinally along your track. You will have a Z shape of like ballast basically sinking into your sub ballast. The schematic talks about soft clay, but this is not necessarily even non-plastic silt with sand or stiff to hard clays. Again, if the thickness is not designed properly, the amount of loads that you can get here might be excessive. So the objective of this method is basically to estimate the granular material thickness that limits or that addresses two criteria, the plastic strains and the deformations. You want to keep them to an allowable limit. Now, the criteria for allowable strains and deformations, I personally like to link them to the stress ratio if we're dealing with soils in general. So how much deviatoric stress you're getting versus how much compressive strength you're expecting your soil to give you. And also there is like design codes, project specific standards, manuals that provide guidelines. And with guidelines, you have numbers to start with, but they are not necessarily, sometimes they are stringent, more than needed, or sometimes they are a bit loose. So you need to just check what's your guidelines are and the criteria that you need to pick your allowable strains and deformations. Just briefly here, if you want to design for like against mode 1 failure, which is the plastic strain, you want to make sure that the epsilon P, like the plastic strains you're getting on your subgrade, is lower than the allowable plastic strains that you specified. So this schematic here, you have the traffic conditions. So again, we talked about the wheel loading, we talked about the repetitive loading, and from that you get your design load and the equivalent number if needed. Equivalent number is used when you have a multi-purpose tracks where you have locomotives passing by, you have passenger trains, and you have also freight trains. So at that point, you kind of need to do a little bit more of digging to get an equivalent repetitive loading, considering how heavy and light each trip might be. And then your design criteria is your plastic strains. And from your plastic strains, you can decide on an allowable stress ratio. Subgrade characteristics, we talked about this: soil type, your compressive strength. That's when your geotechnical sense, I guess, kicks in, and you have to pick up a number that you feel comfortable to load your soil to. Resilient modulus, one of the challenging parameters. There is a lot in the literature about the best way to simulate the resilient modulus. I haven't seen resilient modulus testing being done specifically. I guess part of it is it's very research oriented. So unfortunately, in the practice, people tend to get the resilient from some other parameters. But maybe something I came across was heavy correlations between the resilient modulus and the unconfined compressive strength. And again, don't think about the unconfined compressive strength as test exclusively for like clay only. It can also be handy in an intermixed soils where you have enough cohesion and consistency. So you can always rely on this when you're dealing with silt clay or like silt clay like materials to get a sense of your resilient modulus. The granular material resilient modulus are usually given in your design specifications. These are target resilient modulus, usually significantly higher than the soils, just because of the crushed rock nature that you're dealing with for your granular material. You take all this, you have your allowable deviatoric stress. You go through charts. I'll show you this in a bit. You get your strain influence, and from there you can get your granular thickness. So the approach sounds pretty straightforward. However, you need to be aware of all the kinks and all the swerves as you develop these parameters till you get to your like granular material or granular layer thickness. This is where you have to do a little bit more interpretation and look at your data to be able to decide on which deviatoric stress you're comfortable with. How much would that mean in terms of strains and strain influence factor? And then what would be your granular material thickness? So this is just an example I digged from one of my old projects, but I basically, the equation they provided here correlates your plastic strain to the stress ratio. A, M, and B, these are your stress, shear strength parameters. Lee et al., they have done a lot of work as well, trying to specify, again, guidance as to how to get the A, the M, the B from a quite intensive database. The good thing is you can always have enough testing from like your project specific testing, and you can actually extend on what they did to come up with your own parameters of A, M, and B. I'm not gonna touch on this, but they have a paper that's very detailed, and it can help you actually understand the significance of each of these parameters. And then you see here with the stress ratio, you have a cumulative strain, right? This is basically a soil that's yielding, right? As we go with like higher stress ratio close to 1, you're basically reaching the maximum capacity of your soil. You're getting a very high plastic strain, and you can say, okay, if I am comfortable with a stress ratio of half, so this means the deviatoric stress acting on my subgrade is half of my compressive capacity. This would reflect to a cumulative strain or plastic strain of, let's say, 2%. So this is your EP right there. The key is getting an appropriate representation of how your soil will react under different stress ratios. And then in this chart here, you see that's a correlation between the influence factor and the granular layer thickness H over L for different subgrade stiffnesses. So basically with your I sub epsilon, which is your influence factor that you got, knowing your sigma D, knowing your dynamic load, the A and the L are just numerical factors that they developed for this method. So I believe the A was 0.5 and the L was 0.15, if I'm not mistaken. And then with this, you do, curve fitting, you see where you fall within these A, B, C, D, depending on the resilient modulus of your subgrade, and then you get your granular thickness. And that's basically the combined thickness of your ballast and sub-ballast. Similarly, for mode 2, we're dealing with the same problem, but here we're talking plastic deformations instead of strains. And you follow the same approach. By now, you don't need to touch this because you're dealing with the same track bed. So the beauty is once you have your strain, you can always go and look for your deformation influence factor, and then you can get your granular thickness. Equations here for the plastic strain. The way they deal with the plastic strain is a little bit conservative. If you try and solve the same problem using a finite element analysis, you will realize that the plastic strain is usually conservative because they just link the strain to the thickness of your subgrade material. And again, as a geotechnical engineer, you're the one who can decide on the effective or the depth of influence of your embankment. So how much would your T, like the subgrade thickness, and then you get your H over L as well. In here, they also linked the plastic deformation to the thickness of your subgrade, because the thicker your subgrade is, the more likely that you will need a thicker granular material to disperse that pressure. And that's what this charts are trying to say. So for A compared to G, for instance, right, where you have T over L of 2 versus T over L of 36. So again, you have to always keep these things in mind, follow like the engineering sense and your understanding of the stress distribution and the factors that would govern your stress distribution. Some of the additional geotechnical aspects now, hopefully that you follow these steps, you're comfortable with your thickness of the ballast / subballast, you know what granular type that you're gonna use. Then comes in additional aspects that as a geotechnical engineer you're expected to have a look at, right? The alignment grading, this is something that you often work with the civil designers. Cut versus fill, how much fill you're happy with or comfortable with, giving how strong or weak your soil is, the subgrade soil. The cut sections recommendations related to like excavation when you have a cut grade versus a fill grade. Subgrade preparation, so the compaction, you always need to specify the compaction effort. It's always a very good idea to have test pits from like nearby borrow sources or like locations where you think the soil might be good to be used for backfilling, and have this data within your recommendations, or at least think about them from a sense of like how much compaction you really need, the available equipments, and how much effort needed to get to your desired maximum dry density and optimum moisture content. Topsoil stripping and like removal of deleterious material. The settlements is also here a significant issue, especially if you're dealing with clay-like materials or soft deposits. So know your consolidation parameters, have enough consolidation testing to be able to assess your OCR values, your C sub C, compressibility. As a matter of fact, the compressibility can actually help you get the constraint modulus. If you do your construction during like the fall/winter weather, you don't expect your immediate settlement to happen, right? When the soil starts to thaw, that's when you start seeing your settlements. So understanding the timeline and how the construction activities are affected by when you start your construction and when you end it is also very important. Um, Drainage requirements, very important. Again, often overlooked by geotechnical engineers. Geotextiles is very important to be used for bridging when you have like areas of soft pockets along your alignments, and also to improve your drainage requirements. French drains and peripheral pipes often recommended, and you should make sure that they are reflected in the civil drawings. Drainage ditches, and the good thing is when you're dealing with a standardized profession, like in railway engineering, for instance, they always have minimum requirements for the dimensions and the width of the drainage ditches, as well as the side slopes to ensure a good surface and subsurface drainage. The last thing you want is, or the least favorable scenario would be water ponding along your rail track or rail alignment. From operational point of view and also from structural geotechnical stability point of view. So you want to make sure that you have like very good to excellent drainage condition all over your alignment. The ballast sub-ballast properties, you have to specify the mechanical properties and the physical properties. The recommendation often includes the gradation. Again, some track standards, they provide guidelines, but you can always rely on local contractors' experience, your understanding of the requirements of the project, and you can tweak these gradations a little bit to kind of make it more economic friendly. For instance, in mining sites, you usually have available quarries, and these quarries are crushed rocks that are ready to be used, um, and you have to tweak your gradation a little bit to make it reflective of the available quarry that you have on site. Fracture faces to increase angularity and ensure like interlocking friction within your ballast, sub-ballast. The fine content usually very, very low, less than maybe 0.5%. In some cases, you're not expected to have any, but depending on the local soil, depending on, again, the project standards, sometimes they allow room for some fine content. So you have to look into that and be aware of how well good, or typically how like good or bad this would be for your design. So in conclusion, I hope by now you guys have realized that the track bed design is part science, part art. Nothing replaces experience, I guess. So the equations are out there, but again, what parameters you should use, and what's the common knowledge, local experience within your project area will always be a key that determine a lot of your design parameters. Be aware of the applicable standards and regulations when you're selecting your track bed thickness and type. The geotechnical recommendations should cover the physical and mechanical requirements. And I have seen this quite often where the report stops at, here is your granular material thickness, and this is your allowable bearing capacity. And they walk away. But in a projects with the railway projects, this will not cut it, because you need to be more specific about any physical or mechanical requirements that you need for a granular material to be acceptable. So I think by this, I just came to the end of the presentation. And yeah, I hope I gave you guys just a sort of a brief overview of the rail bed or the railway track bed design, and a lot of the aspects from a geotechnical point of view that we should be aware of. Thank you.
Thank you, Ahmed, for this amazing lecture. Yeah, amazing presentation.
Thanks.
Anyone have a question? If you have a question, you can unmute and can talk directly. Okay. So Ahmed, I wanted to ask you, are you doing any modeling, any work related with that, or just go to the empirical equations and?
You know, the modeling is always there and open, but it really depends on the project budget and the client's preference. Softwares like the KinTrack, for instance, that's one of the simple, like, semi-empirical models that you can, you know, use to get a sense of the stress distributions that you will get on your soil. I often find it that having a heavily, you know, like finite element modeling for this sort of work, unless there is a necessity from a subgrade point of view, sometimes you tend to be to go way over budget. So that's why in practice, people always tend to rely on empirical equations experience, as well as semi-empirical approaches, if needs be. Yeah.
That's good.
Yep.
Yeah, I agree with that.
So,
okay.
Yeah.
Yeah, thank you, Ahmed. Yeah.
Oh, you guys are welcome. Thank you.
Thank you, everyone, and Ramadan Mubarak. Yeah, this is the end of the day. Welcome to you again. And if you have any suggestion, any comments, please don't hesitate to contact me. And thank you for all of the participants. Yeah, have a good day.